This video gives a detailed methodological and mathematical walkthrough of causal scrubbing, a Redwood Research method for rigorously testing mechanistic interpretability hypotheses. The central goal is to replace ad hoc interpretability validation with a systematic, hypothesis-driven intervention protocol. Most mechanistic interpretability work answers a hard question: how well does this interpretation actually explain the behavior? Traditional checks like zero ablation or mean ablation are useful but often ad hoc, potentially off distribution, and hard to compare across hypotheses. The setup starts with a dataset D over domain X and a behavior function f from X to real numbers. The quantity of interest is the expected behavior under data, E over X from D of f of X. In many applications, f is model loss or a behavior-specific score. A hypothesis is formalized as a triple H equals G, I, C. G is a computational graph implementing f. I is an interpretable computational graph. C is an injective graph homomorphism, mapping interpretation, nodes into model computation nodes. The correspondence does not require exact value decoding from interpretation nodes into activations. Instead, causal scrubbing tests a weaker but operational claim that equivalence classes implied by interpretation nodes align with equivalence classes of the mapped model computations. Causal scrubbing treats a hypothesis as an intervention blacklist. If the hypothesis says some relationship is unimportant, the algorithm aggressively scrubs it by resampling activations. If the hypothesis is right, behavior should be preserved under these maximum allowed perturbations. There are two key intervention types. First, semantic equivalence swaps. Replace activations with those from inputs equivalent under interpretation semantics. Second, unimportant input scrubs. Replace unimportant parent activations with values from random other inputs. Method defines a scrubbed expectation, E scrubbed of H and D, by Monte Carlo sampling from the scrubbing process. For each sampled reference input X, recursively scrub activations according to the hypothesis constraints, evaluate output behavior, then average. The recursive routine works node by node on the interpretation graph. For mapped important parents, sample new inputs agreeing on the relevant interpretation value and recurse. For unmapped parents, use a random input and patch activations directly. Then run the node function from these assembled inputs. A subtle implementation detail is tying randomness among unimportant parents of the same node. Using the same random donor input for that set avoids artifacts due purely to representation choices in how the graph is decomposed. The main validation metric compares scrubbed and original behavior. If E scrubbed approximately equals the original expectation E over D of F, the hypothesis is considered faithful for that dataset and behavior definition. Why resampling instead of zero or mean ablation? Because the intended claim is usually information irrelevance, not distribution destruction. Resampling keeps module activations on distribution while breaking input-specific information channels. Distributional argument is, keep what should matter according to the hypothesis and randomize what should not. This is analogous to conditional randomization in causal inference, where nuisance pathways are broken while preserving baseline statistics. In the parenthesis balance model, causal scrubbing is used to test increasingly specific claims about head-level mechanisms. As hypotheses become more specific, more layered scrubs are induced, and recovered performance drops, revealing where mechanistic claims are incomplete. In the induction study on a two-layer, attention-only model, a naive hypothesis recovers limited performance. Iteratively expanding pathways and dependencies improves recovery substantially, demonstrating the method's utility for hypothesis refinement loops. A major methodological benefit is interloop integration. Researchers can start with broad hypotheses that recover behavior, then progressively tighten mechanistic claims while monitoring degradation in scrubbed performance. The post is explicit about limitations. First, swaps are exact class only, which is strict for continuous features. Second, tests are dataset limited. If no matching donor examples exist, relevant swaps cannot be evaluated. Third, correlated features can confound attribution. Importantly, passing the test does not guarantee true or complete explanation. Incomplete hypotheses can still score well if omitted mechanisms are correlated or inhibitory effects are not challenged by the sampled interventions. The authors discuss generalized causal scrubbing, where hypotheses define non-uniform swap distributions. This gives a continuous hypothesis space, potentially enabling optimization-based search, but introduces conceptual questions about principled composition and semantics. Alignment relevance is twofold. Directly, it strengthens evaluation of human-proposed mechanistic interpretations. Indirectly, it can serve as a mechanical scoring procedure inside automated or AI-assisted explanation search, where full human semantic understanding is not required. Mathematically, the method can be summarized as constrained stochastic intervention. Define a hypothesis-conditioned distribution over activation, rewrites that preserve declared semantics and randomize declared irrelevancies. Then estimate expected behavior under this intervention distribution and compare to baseline expectation. For practical use, a good checklist is: define behavior and dataset clearly, formalize hypothesis tuple, run high-sample scrubbing with ablation diagnostics, stress test with adversarial refinements, and report both recovery and known blind spots. Final takeaway: causal scrubbing does not solve interpretability by itself, but it upgrades interpretability evaluation from informal ablation anecdotes to a principled, recursively constructed testing framework that makes mechanistic claims more comparable, falsifiable, and improvable.